Hello everybody, my name is Xingdao Du. The paper is called Phonotype, Localization, Reconstruction, Post-Processing with Robust Stem Extraction Algorithm. We are coming from National Taiwan University. This is the outline. I will give the introduction, system description, plant reconstruction procedure, and stem extraction algorithm and its results. And then a short summary is given. Japanese food is very famous. The type of food is also varies. In my memory, Japanese food is usually expensive, like the luxury melons. But why it's so expensive? The Live Japan gave us the criteria, like color, sweetness, and size. If the farmer wants more perfect, they need to pay a lot of attention on it. Therefore, our scenario of this paper is using the precision agriculture on high perfect crop and labor-intensive industrial. I will give you the system description here. This is our proposed system. We have a depth camera called RealSense D435, and the robotic manipulator is called TM5900. And then live made UGV, which is not shown in this figure. Also, we are using the ROS system, robotic operating system, as the integrated platform, and the definition of frames shows on the right hand side. This is a flowchart of our proposed system. First, we have a plant scheduler, which is not part of this paper. It outputs the next scanned plant. And then the UGV move to the target plant. After that, the system needs to know the location of the plant, and we are using the Aruko board to provide the absolute position. Once the plant location is known, the robot will reconstruct the plant. We got the point cloud of the plant. After that, the mean stem will be extracted using SEA. Stem is very important because in most cases, plant organs are growing from mean stem. Once we know that, we can exclude more advanced applications. So let's move on to marker-based plant localization. First, the robotic manipulator is scanning for sector area to find the Aruko marker. Once the location of the marker is determined, the robot stops its movement, and then a closer viewpoint will be planted to get an accurate reading. This is because the accuracy of the marker reading is dependent on the distance between camera and marker. After that, the readings will be averaged. Finally, we got a transformation matrix between the base frame and plant frame. And these three transformations are the transformation from the base to camera, which calculated using the forward kinematics, and this is what we get from this formula. And the third one is the constant. So how we deal with the raw print cloud? We have two constraints to deal with the original print cloud. Initially, we use a bounding box as a filter. Any points inside this box will be left, and others will be removed. Like this. This is the result. And to distinguish the plant tissue from the complex background, we're using a color format, HSV, to fit specific hues. In this case, we set the hue from 40 to 70 degrees. Any irrelevant parts will be removed. And then the robotic manipulator starts to reconstruct entire print cloud. Because of the error from camera or environment, registration is needed. This GIF shows how iterative closed print, or ICP, method works. Two cases shows that the method could perfectly register two print cloud. Let's move on to SEA. The stem extraction is our core algorithm in proposed system. It have totally 4 steps. The first step is to generate the starting searching point. To avoid unnecessary computational cost, we firstly downsample the original cloud. And then we using the bottom part of the downsampled part and downsample this cloud again to generate some starting searching points. The red points are starting searching points. After that, the iterative next sprint searching. In this step, the algorithm starts from SSP0 and find the best next starting point. This is the start starting point 0, and we want to find the nearest point, and we want to find the best point as the next starting point. For example, this red circle will be selected, but why we select this point will be introduced later, and iteratively this process will find another one and another one. So consider the cultivating condition and heuristic sense. Two parameters are used in SEA, which are distance and z-tilde angle between p-start and p-next. Because we designed two activation function of distance and angle, which are quadratic and exponential. For distance, we don't want select a much duration point. It means the large distance or small distance. We want to find the intermediate distance. And for angle, we don't want to, because the plant is cultivated upward, so we don't want this angle is too much. So we design this activation function. Simply multiply two functions, we get a gain function curve here. As we mentioned, the condition pair will be a score. This score is located on this surface. After that, the result of SEA is sparse, like this line. So we need a densified stem cloud for more detail. We connect adjacent points as a line and find the perpendicular distance between arbitrary points and this line. Any point of distance is smaller than a threshold will be considered as a part of this stem. So this is the formula of the line, and this is the formula of the distance. So this is the result of the densified stem cloud. So once we get the densified cloud, we need some quotation to evaluate whether the result is good or not. 3 of them are positive correlated, which are stem point cloud size, stem point stem, plant height ratio, stem overall growth direction, which use the technique called PCA, and one is negative correlation, is called stem cluster size. And we just simply multiplying these 4 parameters, and we got the final score as M stem. So let's show some experimental results here. First step, we get the starting searching point using downsample technique. The red point means the start searching point. And then, in step 2, the detail figure shows how our algorithm works. The green lines represent this candidate pair, which the score is larger than threshold, vice versa. In step 3, the stem has been densified. The magenta points are densified cloud. In step 4, we doing the evaluation of extraction stem candidates. In this case, we got 8 candidates, and the score are shown in this table. The first stem is about 240 score, which is the best and selected for final stem. Also, we did several experiments to verify the robustness of the proposed algorithm. The results shows the SEA works well under intact point cloud or in imperfect point cloud. To explain that, we use one plant in our lab and repeat 3 times. The first one is non-occluding condition, and the other 2 cases are occluded by leaf. The results shows that the algorithm is robust. In each condition, the algorithm could generate a stem. In summary, in our proposed method, our system could automatically locate the position of plant root. After that, the system plans several viewpoints to reconstruct the plant. Once we got the plant point cloud, the most possible stem will be generated using SEA, which is robust enough to overcome the occluding condition. This method in this paper will be a good foundation for future applications. Thank you for attention.